Okay, so I think we'll start. Good afternoon, everybody. Before we start with the lecture, a few words about the project, which is part of the what used to be the simulation sessions. So some of you already started drawing the schematics for the project, the magnetic field sensor last week. The others will start this week. And then in the following 2 weeks are devoted to the layout, and then hopefully we find the possibility to do the assembly of the project in the last 2 weeks. We're not sure yet how this will work under Corona conditions, but we'll let you know in due time. Before you start the layout, please send your KiCad project files of the schematic with a bit of documentation, like screenshots and some comments, to Stefan. The email address is on this slide. Please also ask any questions that you might have. He will try to review your schematic to make sure that it's fine for starting the layout, and he will try to answer your questions. Okay, so let's move to the today's lecture. So the plan for today is to start with a short recap of last week's lecture on transistors. We'll then assemble a more realistic small signal equivalent circuit and use it to analyze the emitter follower in a bit more detail than we have before. Then the next item is the so-called common or grounded emitter amplifier. We'll go through the principle of operation and then details of working point setting and the so-called emitter degeneration. Finally, we discuss speed of such circuits, while up to there we only looked at DC behavior, or mostly at DC behavior, and we'll discuss the role of junction capacitances inside the transistor and construct a high-frequency small signal equivalent circuit. Okay, so here's the recap of the bipolar junction transistor. So there are two types of transistors, the NPN transistor and the PNP transistor. They're mostly interchangeable, but the polarities are different. So they both have in common that they have three terminals: the emitter, the base, and the collector. And in both cases, the base emitter diode, the current in the voltage across the base emitter diode controls the current, and hence the current in the base, and hence the current in the collector. The direction of this diode is different in the NPN and the PNP transistor. So what makes this transistor useful, of course, is that the collector current is a large multiple of the base current. So the current gain beta is a number that is much larger than 1. Oops. Okay. Sorry, I have some audio problems here. Okay, so the current gain is for bipolar transistors typically between 30 and a few hundred. Which means that the base current, sorry, I have to change the microphone here. Okay, sorry for the short interruption. So what makes this transistor useful is the fact that the base current is much smaller than the collector current, so we can control a large current with a small current. The emitter current is the sum of the collector and the base current, so it's a factor beta plus 1 times the base current. And for these, for the collector and the base current, we have this usual diode characteristic. So for the collector, it's beta times the saturation current, and then this diode factor, where in most cases we can neglect the constant term here and just have the exponential. And this leads to what we know from the diodes already, that the base emitter voltage is typically of the order of 0.6 or 0.7 volts. The other interesting part is that the collector current as a function of the collector emitter voltage, so from here to here, is roughly constant. So this is shown here. If you look at it as a function of the collector emitter voltage, the current for constant the collector current for constant base current or constant base emitter voltage changes only very little. There is a small deviation due to the early effect. The most important small signal parameters are the so-called transconductance, which is the modulation of the collector current by the base emitter voltage. So if we change the collector, so the base emitter voltage here, then the transconductance tells us how much the collector current changes as a function of that. So this is called GM. It's the derivative of the collector current with respect to the base emitter voltage. And with this exponential behavior, turns out to be the ratio of the collector current divided by the thermal voltage. This is, of course, a function of the working point. So when you are at low currents or low VBE, then the slope is much smaller than when you go to higher currents or higher VBE. The other important characteristic or parameter is the so-called emitter resistance. And this tells you how the current changes when you change the base emitter voltage, which is kind of similar, of course. So the base emitter voltage is defined as the derivative of VBE with respect to the emitter current, and turns out to be simply the thermal voltage divided by the emitter current. And so this is 25 milliohms over the collector current, roughly, if we assume that the collector current and the emitter current are roughly the same. This simply means that the emitter resistance is 1 over GM multiplied by a factor that is very close to 1. And it also, since it's roughly the same thing, changes a lot as a function of the emitter current in this case. So we have modeled the transistor in the emitter follower simply by a resistor between the base and the emitter last week, and that was okay to describe the gain of this circuit. So how much does this point change when we change the voltage at the input? It seems to behave like a voltage divider between the load resistor and the emitter resistor, which is, I should say again, is not an actual resistor. It's just the slope of this curve. Still, we can treat it as if it was a resistor using these equivalent circuits. It also gave us the correct time constant when we operated this with a capacitive load. So if we add a capacitive load here, then this model predicts the correct time constant that we actually observe, namely the parallel of the emitter resistance and the load resistance multiplied by this capacitance. And since in most cases this emitter resistance is much smaller than the load resistance, or should be smaller than the load resistance, this is approximately the RC. Sorry, this is wrong. This should be RE. Sorry, I'll fix that. So it's the transistor determines the speed of the circuit. Now for general use, this picture is too simple because clearly certain things are missing. It doesn't give you the correct base current, and it doesn't have anything to say about the collector current. So in the next slides, we'll start developing a better picture. So, and this is done by adding a current source between the base and the collector, which is controlled by the base emitter voltage. So the proportionality factor is, of course, GM. Or if you want to look at it as a current-controlled current source, it'll be beta times the base current. Now we can check whether this picture is now consistent with all our transistor characteristics. So for a real transistor here on the left, we have, of course, that the sum of collector and base current is the emitter current. And this obviously also holds in this picture. So the emitter current is the sum of collector current and base current. The GM is this derivative here. And of course, also in the small signal picture, we have GM by definition being the ratio of the small signal current divided by the small signal voltage, and these are changes of the actual large signal voltage. So this is the same as the derivative here. So this is okay. The current amplification is given as the ratio of collector current and base current is beta, and this we have to check here. Now the ratio of the small signal current divided by the small signal collector current over the small signal base current is the small signal IC divided by the difference now, emitter current minus collector current, which is the base current. And here we can now use for the collector current GM times VBE. And here we have the emitter current, which is the base voltage, so VBE divided by RE, minus the collector current, which is again GM times VBE. This is not obviously the same, so we have to do a bit of math. VBE cancels, and we're left with this expression here. So now we have to see whether beta is the same as this term. And it is a relation now between this RE, which is a function of the emitter voltage, and beta and GM, which are functions of the collector voltage. So we start with this relation between collector voltage, emitter current, and collector and base current. So we say the base current is 1 over beta times the collector current. So this gives us the ratio of emitter current and collector current. Now the emitter resistance is this derivative here, and then we can use the chain rule. So we have the derivative of the collector current with respect to the emitter current, and the derivative times the derivative of the base emitter voltage by the collector current. And this is simply this ratio here, 1 over this ratio, so beta over beta plus 1, and this is by definition 1 over GM. So we can rearrange terms a little bit, and then we have GM times RE times beta plus 1 equals beta. We need to shuffle this around to find that beta is indeed GM times RE minus 1 minus GM times RE. So even here we have checked that the small signal and the large signal model are equivalent. So we can use this now to analyze circuits. Before we do this, I would like to mention that there is another equivalent circuit which does the same thing. We have seen that one can, instead of looking at the emitter voltage, one can also look at the base emitter voltage here. They are equivalent if we get for the same currents the same base emitter voltage, and this is easy to see. So on the left-hand side, the base emitter voltage is the emitter current times this resistor, and on the right-hand side, the base emitter voltage is the base current times this resistor. So it's the voltage drops across these resistors must be the same for the same currents, and this simply means that RBE is equal to IE times RE over IB, and this ratio here is beta plus 1. So the two pictures are consistent if RBE is beta plus 1 times RE. So you can also read this that the resistance at the base appears to be by this factor larger than the emitter than the resistance at the emitter because of the current gain of the transistor. Now these two have names. The first one, where you have the base emitter resistor, is called the pi model. It is often shown in the style on the right-hand side, where you have which is inspired by the two-port picture, where you have base and emitter on the left-hand side and collector and emitter on the right-hand side. And these two drawings are exactly equivalent, just arranged in a slightly different way. And because this is called the pi model, to some people this seems to look like a pi. This resistor in this case is also often named R pi. We'll use the RBE convention in this lecture here. The other thing is called T model because it looks more like a T, so the resistor here is between these two. And the two-port style drawing would be like this. So most of the time we'll be using the pi model. So the thing that's still missing in our pi model is the early effect, but we will include that now. So if we have the model without the early effect, then the collector current is simply constant Gm times VBE and independent of VCE. This is shown here. So you have these curves that show the current as a function of VCE, which become in this active region. And of course, the small signal models will only work in the active region. They're never used in the saturation region. So here, the current grows as Gm times VBE and is independent of VCE. Now this changes, of course, when we turn on the early effect. Now there's, as a function of VCE, an additional current increase from the early effect. So if we go a little bit higher in VCE, we'll see an additional increase that comes from the slope of this. And the proportionality factor is called GO, or output conductance. And we can model this in our picture by putting a second current source parallel to the first one. So this sum here is now the sum of two current sources. This one is Gm times VBE, which is the usual amplification, and this one is GO times VCE, which is the early effect. So this current source now gives us a voltage which is strictly proportional to, it gives us current which is strictly proportional to the voltage between the two ports of this current source. So this is different for GM, of course. Here we have a current that is proportional to the voltage at a different port, but here we simply have a current proportional to the current to the voltage between the two things. And so we can simply replace this by a resistor which has the same characteristics. And the value of this resistor we will call RCE. It's also sometimes called RO, which is simply the inverse of the output conductance. So our small signal model now looks like this, and the current in the small signal picture can be written as Gm times VBE plus 1 over RCE times VCE. The relation between the small signal RCE and the early voltage is still missing. So this is the definition. It's this derivative for constant base emitter voltage and constant current. And we have written this parametrization of the collector current with the early effect. So it's beta times the base current multiplied by this factor here, where we have the collector emitter voltage over VA, the early voltage. So the derivative of this is GO. So this term here, and that simply gives us a 1 over the early voltage multiplied by beta times the base current, which I assume to be current in this derivative. And then if we neglect the plus 1 here, so for relatively large early voltages, we can simply write this one here as the current voltage, the collector current divided by the early voltage. And for G, this is for the output conductance, and hence the inverse is the collector emitter resistance, which is early voltage divided by collector current. So for typical bipolar transistors, this is like 100 volt divided by 10 milliamps, just to have an order of magnitude. So this is 10 kilo ohms. So it's a relatively large resistance, where the emitter resistance on the other hand is extremely small, few ohms typically. Okay, so this now is our completed hybrid pi model with the early effect. Let's go through it once more. We have the base emitter diode, which is modeled in the small signal picture by the RBE resistor. We have the collector current modulation, which is given by this current source, and we have the early effect modeled by this resistor here. So this model is very good for DC and low frequency applications. We will later add the junction capacitance models that are needed to describe the behavior of a transistor at high frequencies. So now we move on and reanalyze the emitter follower with this hybrid pi model, including the early effect. We will start with amplification, then look at the input resistance, and finally at the output resistance. So let's start with the amplification. So this is the equivalent circuit. We have here's the pi model equivalent circuit of our transistor. We add a resistor from the emitter to ground. So this is our output now, and this is our input. And in order to determine the gain, we need to know how V out behaves as a function of V in. So let's go through this. The collector and the ground are fixed voltages, and in the small signal picture, where we only look at changes of voltages, being constant means we can just assume that it's zero. So to analyze this, we use Kirchhoff's current rule, and the only node that is non-trivial here is, of course, the base, which is the output. So let's add up the currents here. We have the base current flowing in. We have the collector current, which is beta times the base current flowing in. We have the current flowing through the resistor, which is V out over R, which is flowing out. And we have the current through through RCE, which is again flowing in, and which is VC minus V out divided by RCE. Now we said that the collector current is the collector voltage can be set to 0, so this simplifies to this expression. So here we pull out IB, so it's 1 plus beta times IB minus V out, and then here we have this expression 1 over R plus 1 over RCE. So the last term is conveniently written as R parallel RCE, or 1 over R parallel RCE, and this one, and we replace the base current by the difference of input minus output potential divided by the base emitter resistance. So this is this expression here, and now we have a term that an expression that contains only the input and the output voltage. So we can separate, bring all terms that have the input voltage to the left. So this gives us a beta plus 1 over RBE. And on the right-hand side, we have beta plus 1 over RBE plus 1 over R parallel RCE. So the amplification or voltage gain is the ratio of the two. So this is 1 over this expression, 1 over 1 plus this. So RBE divided by beta plus 1 times the parallel of RCE and R. So this is now obviously slightly different from what we had before, but it's still, you can see that this is an expression that is always slightly less than 1, especially if beta becomes a very large number. We can compare this with the simple picture that we had before without the early effect. There the result here was that the amplification is 1 over 1 plus emitter resistance divided by R, and the emitter resistance can now be is the base emitter resistance divided by beta plus 1, as we've seen before. So this is the term that we have to compare with our new result. So with the early effect, we have this expression. If you compare the two, sorry, and if you compare the two, you see that we've replaced R by RCE parallel to R. At first sight, this may be surprising. Why are these parallel? Because they're not really parallel. But remember that we can take all points that are at constant potential to be at the same potential in a small signal analysis. So in this sense, we could have drawn RCE like this, and then it's obvious that the two are parallel. For the amplification, this is normally unimportant if this resistor that we have at the bottom, which is typically not too large because we want to use the emitter follower to drive small loads, small impedances, so it shouldn't be too large itself. So that this resistor is typically much smaller than RCE, which is usually of the order of 100 kilo ohms. Next, we look at the input resistance of the emitter follower. So the input resistance means how does the input current change when I change the input voltage. So what current do I need to deliver here when I want to change the input by a certain amount? It is defined of the ratio simply as input voltage by input current. Again, we analyze the sum of the currents in the output node. And so these two, the current through the base and the current through the collector, are 1 plus beta times the base current. Sorry. And the two currents that we've seen before through these two resistors are now again simply the output voltage minus RCE parallel to R. So this, as we've discussed before. Now we wanted to have V in and I in, so here we have to get rid of the V out, and so this can be done by taking the voltage drop across the input resistor. So the output voltage is the input voltage minus the voltage drop across this resistor, so V in minus RBE times I in, and this factor remains, of course. So rearranging and sorting the terms, we have 1 plus beta times RBE over RCE parallel R multiplied by I in, and we have minus V in divided by RCE parallel to R times the input voltage. So the input resistance is then simply the ratio of the two. We can multiply it by RCE times parallel R, and then we get simply this expression. So the input resistance is the sum of RBE and beta times the parallel of RCE and R. So this resistance here is multiplied by a large factor and adds to the not so large input resistance. So if beta is large, as it should be for a good transistor, then this term actually dominates, and we get beta times R for the input resistance. So it's not, as you might think, the small RBE input it's not our input resistance, but it's really what we hook up to the output multiplied by the amplification of the transistor. Same now for the output resistance, and then we have everything that we want for such an amplifier. So output resistance means how does the output current change with the output voltage, or vice versa. If I change the output current, how does the output voltage change when I keep the input voltage and the collector voltage constant. Okay, so this is the formal definition. It's the derivative of the output voltage with respect to the input, with respect to the output current, at constant voltage. In small signal terms, simply this ratio. Again, we look at the current balance here, and we have the current flowing from the base is here, V in minus V out divided by RBE, multiplied by beta to add the collector current. So this is this term again, and and we have, just like before, the output voltage divided by RCE over R. But now we want to express it in terms of I out and V out. So we simply add up all the terms that are proportional to V out. V in is constant in this case, so we can just drop it. So we're left with only expressions that are proportional to V out on the right hand side, and this gives us this term here. So our output resistance is simply given by 1 over this term. So it's 1 over RBE times 1 plus beta plus 1 over RCE plus 1 over R. And this looks, of course, like we're having 3 resistors in parallel. So we can write it as R out is the parallel resistance of RBE over 1 plus beta, and RCE and R. And so in most practical, so this is RE, of course. So in most practical cases, we can again neglect RCE here, and we roughly have the parallel value of RE and R. Okay, so now we have what we needed to characterize the emitter follower as an amplifier. Let me summarize here again the 3 ways of looking at this. So the first one on the left-hand side here is the actual physical circuit, which has all the nonlinear properties of the transistor. Now this we replaced by a linearized version that we can use around a working point, which is our small signal equivalent circuit. And the whole thing can now that we have determined the input resistance and the output resistance also be seen as a generic amplifier that has an input resistance given by this resistor and an output resistance and an amplification which is close to 1. So these are two ways of looking at the same thing, and often this one is the most convenient, of course. But to get these values here, you need to analyze the circuit using the small signal analysis. And just to summarize, the emitter follower, of course, has a very high input impedance, which is given by beta times the load resistor, and a very low output impedance, which is the parallel value of the emitter resistance and the load resistance. Because it has high input and low output impedance, it is also called an impedance converter. What is an impedance converter good for? Obviously, when you have an ideal voltage source or an ideal signal source, it will always produce the same output voltage for any type of load that you attach to it. Now, let's say this is our signal source or voltage source. If it's not ideal, it'll have some kind of output resistance. Now, if you attach a load to it, it means that your output value here is no longer independent of the load, but it will actually form a voltage divider between this load resistor and your output resistance. So the output voltage here is reduced by some factor. So when you have a heavy load, which is a small resistance or a low impedance, this will reduce the output swing. Now, if you put an emitter follower in between your not ideal signal source and your load, so this is shown here. This is our emitter follower as an impedance converter. Then you basically replace the load resistance. Sorry, this should not be RL, it should just be R. You replace this resistance by the input resistance of the emitter follower, which is a large number. So this V1 will be very close to 1. Effectively, yes. So if you compare it with this term here, you get basically a reduction of the series resistor divided by 1 over beta. So for a large beta in your emitter follower, you can neglect this term, and this becomes basically unity. And then at the output, you have a small output impedance, so this will also not cause any change of amplitude here, and you can drive your load without further loss. So the total gain, of course, is the product of the divider at the input, the internal amplification, and the divider at the output, which you can determine with the small signal parameters that we've calculated using the small signal equivalent circuit of the transistors. Okay, so how do you use this? Obviously, when you have a high output impedance signal source, like a filter, we've in one of the first lectures, Georg talked about cascading filters, which is problematic sometimes when the following filters act as a load for the preceding filters. So this is one application where you can use such an emitter follower in between. But many sensors also have the same problem, that they have high output resistance and also voltage dividers do the same. On the other hand, you can have a low impedance load, for instance, the well-known 50 ohm cables, which is a very small impedance for many circuits, or you have a power load that you really want to drive with a substantial current. So these are applications where you can use an emitter follower as a very simple option. And in this case, when it's a resistive load, the load itself becomes part of the emitter resistance. So you replace R by R parallel with the load resistance. Okay, so let's move on from the emitter follower now to an amplifier that actually has an amplification that is greater than 1. So far we had amplification of 1 or even less than 1. So now we look at a different transistor configuration called the grounded emitter. Why grounded emitter? Simply because in this case, when it's an NPN transistor, here we have the emitter at ground. The base of the transistor is considered a voltage input, and we connect a load resistance from the collector to the supply voltage here. So the transistor here is supposed to be in the active region. We have a small base emitter voltage. So the base current here now controls the collector current, and the collector current causes a voltage drop across this resistor. So and that in turn sets the output voltage. So the more current flows to the collector, the more this point is pushed down, and so counting from the supply voltage, we are at supply voltage minus RC times IC. Now, if you increase the base emitter voltage to get a higher current, then the voltage drop across this resistor will increase as well, which means that this point is being pushed down. So the higher you go with your input voltage, the further down this node will come. If you go too far, so your current becomes so high that the resistor wants to push this point below the base potential, then you start getting into saturation, and at that point there will be no further increase of the collector current. This is very similar to what we've discussed last time, where we treated it with a current source at the input. This can also be looked at graphically. So the blue curves here show the collector current multiplied by the collector resistance. So it's basically proportional to the collector current as a function of the collector emitter voltage for varying base emitter voltages. So here we go from 600 millivolt to 640 millivolts for the base emitter voltage. So this is the input here. And you see these currents which are almost independent of the collector emitter voltage. Then the resistor current is given by the difference of the collector of the supply voltage minus the output divided by the collector resistance. So this is the red line shown here for 15 volts. So for 15 volts supply voltage, so when the output is 0, you get the maximum current, so VCC divided by R, and when the output reaches 0, you get the minimum current or no current at all, and that is, of course, when the output is 15 volts, so when you go out up to 15 volts here. And For each value of the base emitter voltage, the output is found by of course, by requiring that the collector current and the current through the resistor are equal, unless there's, of course, a load here at the output, which we neglect for the moment. So we have to find for each of these values of the base emitter voltage the intersection point of the blue curve for the transistor and the red curve for the resistor. So you can see here that a relatively small change of the base emitter voltage. Here we have 40 millivolts in base emitter voltage change results then in a huge change of the output voltage. So in this case, roughly 8 volts of difference in the output voltage for 40 millivolts change in the input voltage. So this is a very high gain voltage amplifier. Let's look at this for arbitrary values of the input voltage. So this is shown here. You see the input voltage here and the output voltage here. And what is plotted is this expression here. So the output voltage is the supply voltage minus collector resistance times the transistor collector current. And so when we're in the off region, so the base emitter voltage is less than 0.6 volt, of course the resistor is pulled all the way, the output is pulled all the way up to the supply here at 15 volts. And then when we get into the active region, this term picks up, and this slope here is basically the exponential of the collector current that you see here. And when you go too far, you get into saturation, and the current is basically zero. Sorry, the voltage is basically zero. So this is the region that we're really interested in. So you notice, of course, that you have a relatively small useful input range here. The whole thing is nonlinear, so the slope of this amplifier, it changes as a function of the input voltage. So this is a typical case where you would apply a small signal analysis. So we do this here using, again, our hybrid pi model. Now we add the collector load resistor to our model, and this is now here. And we want to know now, to find the amplification, what is the relation between the input voltage here and the output voltage here, which is the output voltage is the collector voltage of the transistor. So the voltage gain without load the output voltage is this current here, which is Gm times the VBE, multiplied by the combined value of these two resistances, which we can take as parallel, as you can see from this equivalent circuit here. So the gain is simply V out over V in. So this is Gm times the parallel value of the RCE and R and RC. So this means that the largest possible gain that we can get may well be determined by RCE. So if RCE is not, we cannot make our gain arbitrarily large by increasing RCE, because at some point we'll reach a value where RCE becomes larger than, where RC becomes larger than RCE, and then it'll be limited by RCE. So this is like an upper limit. Of course, this is a large value anyway. It just means that you would not operate this amplifier with resistors that are much larger than several kilo ohms. So if you want to get to extremely high gain, at some point you'll be limited by RCE. Okay. I think we'll take the break now and continue in 15 minutes. If you have any questions, you can ask now, or you can ask anytime. Welcome back. We continue with the grounded emitter amplifier. The overall input-output characteristics of this amplifier is shown here again. For this input voltage here between 0 and 1 volt, this is the output voltage, which is, of course, for as long as the transistor is in off region at the supply voltage, 15 volts in this case. Then we have a relatively small region where it drops quickly from 15 volts down to 0. Oh, sorry. Dankeschön. Thank you. Okay, so I'll start again. Welcome back. We continue with the grounded emitter amplifier. The plot here shows the input-output characteristics of the grounded emitter amplifier, which is for input voltages that are less than a diode drop. Here, basically the output is at 15 volts. And then if you go too high, it saturates the transistor. So the active region is here, and the useful range depends, of course, on your collector resistor value. But when you're here, you have a very high voltage gain, but only a small useful range. In this case, 30 millivolts or so, where you can use this high gain. So it's important to set the working point of your amplifier very precisely. If you're a little bit off with your working point, your amplifier will immediately stop working. So one way to set this working point, or the offset for your small signal, would be in principle to directly set it with a constant offset here. And this is of course very delicate. The working point then depends on top of course the fact that you have to dial in this value very precisely. It depends on the supply voltage, because if you change your supply voltage, then the output will simply follow directly the supply voltage, because it's the difference of supply voltage minus the collector current times the collector resistance is missing here. But it's also a strong function of the temperature, and also depends on components variations. So this is not the best way to use this amplifier, and should normally be avoided. Just to illustrate the temperature dependence of such an amplifier here, the collector current has multiple factors here. Each have some temperature dependence. The largest one comes from this from the saturation current, and another large one here comes from this exponential term, where you have the thermal voltage, which is proportional to the temperature. This saturation current doubles roughly for every 8 degrees. We've already seen that for the diode, and the same thing happens for transistors. This increase is partially compensated by this term here, which goes down a little bit, but in the end, the current increases with temperature, which means that our output characteristic shifts by 2 to 3 millivolts per degree of your input voltage. So if you have an amplifier that is biased to work well at, say, 27 degrees, it'll no longer work when you go to minus 15 degrees, for instance. So there's no, between these two temperatures, there's no overlap between the working ranges of the amplifier. So if you want something that is not terribly dependent on the ambient temperature, then you have to do something else. So, and a better way of setting the biasing for such an amplifier is shown here, by using not the base current, but by using not the base voltage, but a base current. And this base current, in the simplest case, can be set with a resistor from the base to the supply voltage. So now the base current is given by the difference of the base potential and the supply voltage divided by this base resistor. Now the base current is only a weak temperature of a weak function of the temperature through temperature changes of the resistor itself and very small changes of the base emitter voltage. So it's relatively stable with respect to temperature. At least the working point. What still remains is, of course, that the collector current itself is a function of beta. So the beta change comes in. And what's even worse is that there are still large variations of beta itself from device to device. So this is still slightly difficult. But if you decide to do it like this, how would you choose the correct value for RB? And one possible choice is to choose it such that you optimize your output range. So you want to put your working point such that your output is roughly in the middle of your active range. So that means that the output for this circuit should be 1/2 the supply voltage, and the output is supply voltage minus beta times base current times RC. So beta times base current is of course the collector current. So this is the output of the amplifier. So this means we can solve this for our base current. Base current is 1/2 VCC divided by RC times beta. And when we know the base current that we want to flow here, we can calculate the resistor value because the voltage from here to here is given by the supply voltage minus the base emitter voltage, which is always roughly 0.7 volt, or we can almost neglect it here. So this is roughly VCC over IB, and then if you plug in this, you get 2 times beta times the collector load resistor. So now we've let's say we've chosen the resistor in this way. Another important aspect is how the output changes as a function of the supply voltage. This is called the power supply rejection ratio. We've seen that when you do voltage biasing, the output follows the input 1-to-1. Now that we use this current biasing with this resistor, this is partially compensated because now the base current is also proportional to the supply voltage, and that pushes down the working point again. So if you take this expression here, the base current is as before, roughly the supply voltage divided by RB, by the base resistor or the bias resistor. Then our output here is given as usual. Now we plug in this term for the base current, and we get this expression here. So VCC minus RC over R bias times beta times the difference of VCC and VBE. And we can separate the terms that are proportional to VCC and the term that is proportional to the input voltage. And now we have VCC is multiplied by, instead of 1, it's multiplied by 1 minus RC over RB times beta. This is called the power supply rejection ratio because it says how much, when this factor is less than 1, how much changes of the input are suppressed in the output, which is of course desired. If you have an amplifier, you don't want the output to depend very strongly on the supply voltage. So if we choose our bias resistor to in such a way as we've done before to maximize the range, then our power supply rejection ratio turns out to be 1/2. Just put in the numbers here. But we can also choose it differently. Namely, if we make it equal to beta times RC, then this term completely vanishes, and then we have a resistor that has a power supply rejection ratio of 0. So the output will be independent of the supply voltage, which is a very nice feature. This is shown here. We have the two cases, sorry, showing the output of this amplifier as a function of the supply voltage. One is sorry, one is for the bias resistor chosen to give us the maximum range, and the other one is the other one. The lines here at the bottom are for the bias resistor chosen to remove the dependence on the power supply voltage, and that actually works here. So this is absolutely flat, while here you have a relatively poor stability, and you also have a large change, sorry, with temperature. So your working point changes a lot with temperature, and that too pretty much disappears when you choose the biasing that is optimized for the PSRR. However, you are here in a position where you have a very small input voltage, which means that your dynamic range, your input range, is also very small, and also your gain is smaller than it would be with the other biasing. So there's always a trade-off that needs to be made here between stability and power supply rejection. It should also be said that this only stabilizes the power supply rejection. It does not stabilize the voltage gain. So the gain is given by the GM of the transistor multiplied by essentially the collector load. And since the GM is proportional to beta, and we say that beta varies a lot, there's no cancellation here. So GM, the amplification of this resistor, of this transistor, is still very unstable with respect to device variations. And now there is a way to change this amplifier to make it also stable against device variations, and this is done with the so-called emitter degeneration resistor. This is shown here. So before we had connected the emitter of the transistor directly to ground. Now we add a resistor here. So you can either see this as an emitter amplifier with a resistor at the emitter, or you see it as an emitter follower with a collector resistor. Doesn't really matter, but most of the time people will look at as an emitter amplifier. And now it turns out that the voltage gain of this is defined by the resistors and not by the transistor itself. So the current that flows through the transistors here is always is more or less the same, and therefore the amplification here is given by the ratio of the collector resistor and the emitter resistor. Now the gain is of course smaller than it is with a pure emitter amplifier. So if you for the emitter amplifier, we had determined the gain to be GM times the collector load, now neglecting the early effect, which is beta times the collector load divided by RBE, or collector load divided by the emitter resistance, RE, where now the RE is not a physical resistor again, but simply the characteristic of the transistor. So what we've done now, we've swapped the small emitter resistor of the transistor for a real resistor that we attached to the emitter. But now the advantage is that this is really determined, the properties of this are really determined by resistors, which are very precise, and this amplifier is now very robust against temperature and transistor variations. So as before, we can set the working point for this with a bias resistor, or some people prefer to use a voltage divider. Then you have a bit more freedom where you can set this, and typically then the input signal is AC coupled. This is very similar to what you do in the during the exercises here. So an interesting thing happens when you make the two resistors equal, and maybe you can think for yourself what happens when you build such an amplifier where emitter and collector resistor have the same value. That's an interesting application. Okay, so let's compare again the two types of emitter amplifiers. So the left one does not have this emitter degradation uh, resistor, and this one gives you the highest possible voltage gain, but you pay the price that you have large device variations. So what your voltage gain actually is scattered a lot from transistor to transistor, and also depends on temperature. So this type of circuit you would use when you need the highest possible gain, but don't really care too much about what the exact value of that gain is. On the other hand, you have this emitter resistor here. Your amplification is now independent of the transistor itself, provided, of course, that the transistor current gain is much larger than 1. Otherwise, this will not work. So the overall voltage gain of this is smaller than for this circuit, but it's much better controlled. And so this type of circuit will be used when you need not the largest possible amplification, but a well-controlled amplification. This we already had. Okay. So far, we've only looked at quasi DC behavior of these transistors, of these resistors. Now we move on and look at the speed of such an amplifier. So we have now here a simulation of an emitter amplifier where you have 50 ohms at the emitter and a kilo ohm at the collector. So naively, you would expect here a voltage gain of 20. This is simulated here in black. You see the voltage at the input, which is a small input step of 100 millivolts. And in red, you see the result at the output. So you see it replicates the step very nicely with an amplification that is very close to 20. It's not exactly 20 because really these 50 ohms add to the emitter output resistance of this transistor, so it's slightly modified from the 50 ohms. But other than that, the red curve here very nicely represents what happens at the input with some time constant. Now, if we add a load to this output here, in this case 100 picofarads, you get to the blue curve, and now you see a clear RC behavior of this output, and the time constant is now given essentially by the value of the collector resistor and the load capacitance, so 0.1 microseconds in this case. Now, we mentioned that most real signal sources are not perfect. They have a certain input resistance, and this type of amplifier is an amplifier that has a very small input resistance. So you need a real good signal source to drive it, because we have this steep characteristic here. Now, let's say if we have an input source in a signal source that has a significant output resistance. We simulated that here. So now the signal goes through a 1 kilo ohm, which is thought to be part of your signal source, of course. And now the output becomes much slower. You can see it here in red for the case of no capacitive load at the output, and in blue for the case with 100 picofarad capacitive load at the output. So, but even the red curve without any load is already substantially slower than it was before. If you compare the red curve here with the red curve here, there's a huge difference. So the difference somehow comes from this resistor. And the question is why? Because we haven't really put any capacitance here that would cause such a slow time constant. And we note that although we use the same step here, already the voltage at the base looks as if it was much slower. So the output is slow even for the no capacitive load case, the red curve, but the same kind of slow time constant is already apparent at the base of the transistor. So we can analyze this a little bit, looking now at we blow up the volume here, the region here, and look closely at the the voltage at the base. This is shown here now on a different scale, of course. So there's a voltage step from roughly 0.98 volt to 1.08 volts here. And you can analyze the time constants here, and using the 10 to 90 times, for instance. So to get from 10 to 90 here, 10% to 90% is roughly 0.27 microseconds here. The time is in microseconds. You can convert that to a time constant, an RC time constant, by dividing by the logarithm of 9. So this is a time constant of 0.13 microseconds. Or 130 nanoseconds. So this looks like your 1 kilo ohm looks into a capacitance of 130 picofarads. So the question is, where do we have these 130 picofarads, even if there's nothing connected to the output? And the answer is, of course, that these are the junction capacitances of the transistor. So these play a very important role for the speed of your circuit. And maybe you remember that from the diodes, that every diode has a junction capacitance, and since this transistor can be viewed as a pair of two diodes, we can certainly expect to have this type of capacitances between the base and the emitter, and the base and the collector. So now we modify this amplifier a little bit just for demonstration. Obviously, when we remove the collector resistor, it's not an amplifier anymore. But just to see what happens when we do this, we look at the base voltage again. So now this is the base voltage that we had before with the collector resistor. Now we remove the collector resistor, and all of a sudden the input is fast again. So that is interesting. So we remove the resistor, and it looks like the capacitance went away. And this effect is called the Miller effect. So where does it come from? When we have the resistor here, it means that when the input goes down by a certain amount, the output goes up by a multiple of this. So which is the amplification. So whenever we have a certain change of the input voltage, delta V in, then the output voltage changes by minus A times delta V in. So the voltage across this capacitor, which is output voltage minus input voltage, is delta V out minus delta V in is minus A plus 1 times the change of the input voltage. So whatever input voltage change we make is amplified by a factor A plus 1 when you in terms of the voltage across this capacitor. Now, obviously, if you change the voltage across the capacitor by a certain amount, then the charge you need a certain amount of charge, which is proportional to this capacitor. And now, if you amplify your voltage by this factor, that means that the charge that you need to pump into this capacitor also is amplified by a factor A. So effectively, from this point here, the capacitance between collector and base looks as if it was multiplied by a factor A plus 1, and this multiplied collectors multiplied capacitance, so this multiplied by the gain is called the Miller capacitance, and the whole thing is called the Miller effect. So the base collector capacitance appears to be increased by the amplification. This is very important. It appears in all kinds of amplifiers, not just in this one. And now, of course, this Miller capacitance forms the RC filter with the source impedance, the series resistors on the previous page, and makes the amplifier slow. So this has nothing to do with what happens at the output. This is really the internal capacitance of your transistor multiplied by the gain of your circuit makes this slow, and this configuration is therefore not suitable for very high frequency applications. We will, in the next lecture, see circuits that work around this. But now let's look a bit more into what happens here. there's also a capacitance between the base and the emitter. But here the situation is a little different. Whenever we move the base into one direction, the emitter follows essentially. So this is the famous emitter follower, of course. So the voltage across the base emitter capacitor is not amplified by any gain. In fact, it's reduced because of the emitter follower effect. So this is sort of an inverse Miller effect. So for the speed of the amplifier, the capacitance at the collector is much more important, at least in this transistor configuration. So to look at this a bit more quantitatively, we again turn to a small signal equivalent model. So we take the hybrid pi model as from before, where we had these two resistors and the current source, and now we add the capacitance CBC between the base and the collector, and CBE between the base and the emitter. So the CBC gives rise to the Miller effect that we've seen, and the CBE does not usually have any Miller effect, because in whatever circuit you do with a transistor, the base emitter voltage never changes very much. It's always close to this diode drop of 0.6, 0.7 volts. However, when you go to high frequencies, both of these kind of steal AC current from the base. So when you come in here with a high frequency current, you open these capacitors, open a parasitic path for this current, and that will eventually reduce your current gain. So while at DC, the current can only go through here and is amplified by your transistor, now you need additional base current to have the same effect at the output, because some of the current will just go through these capacitors in an AC picture. So we can expect this current gain to become a function of the frequency. So what we will try to analyze now with this small signal equivalent circuit is the current gain for constant collector potential. So we take this equivalent picture here. We ignore for the moment the early effect, so we don't have the RCE here for simplicity, and we send in a frequency-dependent base current here, and want to know what is the collector current for constant collector potential. And the amplification that we're looking for is, of course, the ratio between collector current and base current, which at DC is called beta. So we now do an AC analysis using complex impedances. So we will not try to write down a differential equation this time, but we use the complex impedances for these capacitors. So let's look at the current on the collector side first. So we have this current, which divides up into the current that flows through this current source. So it's GM times VB, and then there's the current coming from this side, which is given by VBE minus 0 divided by the complex impedance of this capacitor. And the complex impedance of a capacitor is 1 over I omega CBC. The I here, of course, being the complex unit and not a current. So because we also use I for currents, there's a small risk for confusion. That's why mainly in engineering people prefer to write J now for the complex unit. But I think it should be clear when I is a current and when I is a complex number. Okay, the same thing on the other side for the base current. So the base current is given by, it divides up by the current through this resistor, so it's VBE over RBE, and then the current through the collector, through the base emitter capacitance, so it's VBE over the complex impedance of this one, which is again simply 1 over I omega CBE. And the third term is, of course, the current through this capacitance, which is the same as before with the opposite sign. So VBE over ZBC. So we want to know the ratio of the two, and we notice that all terms are proportional to VBE, so we can cancel it immediately, which leaves us with collector current over base current being this expression here. So we have Gm minus I omega CBC from this term here, and there we have 1 over RBE plus I omega, and then we have CBC plus CBE. So the sum of the two capacitances. So we pull this term, Gm times RBE, out of this quotient of this ratio, because this is simply the DC beta. So we have the DC beta, and what's left here is 1 minus I omega CBC over Gm, and divided by 1 plus I omega, the sum of the two, multiplied by RBE. So we have the DC current amplification multiplied now by a frequency-dependent factor. And so here we have the similar capacitances. So here's CBC and here's CBE. In this case, we have divided by Gm. So this is the much smaller contribution usually, and most of the time this one is more important. So this term will always be much larger than that term. So we can schematically draw this here in this so-called Bode plot, where you look at the current gain or the ratio of the collector over the base current as a function of the frequency in a log-log representation. So here's the logarithm of the frequency, here's the logarithm of this ratio. And if you go into the range where the frequency is small towards DC, then of course this here becomes a constant 1, and you're left with the normal amplification as you expect. Now, at the point where this term here becomes sizable and can no longer be neglected with respect to 1, say at the point where it is equal to 1, this starts to turn over, and from there on we will see a decrease of the gain, which is linear in frequency. So it's 1 over frequency times Gm over omega times the sum of the two capacitances. And the point where this happens is, of course, when this here is equal to 1, and this is called the cutoff frequency or the knee frequency. So where omega is equal to 1 over RBE times CBC or CBE. And now as this falls with 1 over frequency, which in a log-log plot is of course a straight line that you know from the Bode plots, at some point the gain, the net gain, which is the product of this factor and the initial gain, drops to 1. And this is called the unity gain frequency, and it somehow characterizes your amplifier. If you go further in frequency, then some other things happen, and eventually this, at very high frequency, this term will also become important. But already at this point, clearly your amplifier stopped working completely. So from now on, you have an amplifier that doesn't have any gain anymore. So the point where this happens is called the transition frequency. So this is here. So this point where Gm over CBC plus CB is the transition frequency, or where the gain drops to unity. It is obviously working point dependent. So because Gm is a function of the collector current. This is a frequency in radian. In terms of normal frequencies, you will of course multiply this by 1 over 2 pi, and then it's called the transition frequency. Sorry, this is typically in the range of several megahertz up to gigahertz for the fastest bipolar transistors. So bipolar transistors can be extremely fast, and Ft is sort of a number that characterizes how fast you get. However, in most cases, practically useful are only situations where you're much below this. this term, this frequency. So you will never really operate your circuit near the point where the gain dropped to 1. Okay, let's do a simulation here now of an emitter follower, and we look at the currents. So this is our circuit, a simple emitter follower, the transistor, 100 ohm load, 15 volt supply voltage. We bias it to 10 milliamps. So if you downloaded the script yesterday, you have a wrong number here. Then so this was done with 10 milliamps. So our working point is then obviously at 10 milliamps times 100 ohms plus the diode drop. So here you're at roughly 1.7 volts, and you make small variations about this point, and then plot the ratio of the current at the base divided by the current at the collector. So in here you find that this at low frequency you find the DC behavior. You get a ratio of about 220 or so, and this remains constant up to about a megahertz when you see that this starts dropping off. This is the knee point, and then you see this this decrease of the current and the point where the gain drops to unity is reached roughly at 300 megahertz. So this plot shows both emitter and collector current, and they are of course roughly the same. For low frequency, at high frequency you start that they diverge a bit, and at that point basically you stop operating the transistor as an amplifier, and all you see here are now capacitive couplings from the input to the output. So if you plot the gain of this circuit without any series resistors, you get the red curve here, and this appears to be working far beyond 1 megahertz. So it's the output still appears to follow the input. However, like I said, the transistor doesn't do this anymore. This is all to capacitive coupling. So the fact that the transistor doesn't really do anything anymore shows up as an increased input resistance. So now, if we have now a realistic current source, a signal source with some output resistance of, let's say, 100 ohms, you get the blue curve here, and you see that this now drops off as the transistor stops working. Okay. Before we now look at this in a numerical example, a short reminder about capacitances at p-n junctions in general. Maybe you remember this slide from the diode lecture. So there are two contributions to this junction capacitance, or to this capacitance at a junction, I should say. In forward bias, the diffusion capacitance dominates. This is shown here as the blue curve. This is due to the charge storage. The injected charges are stored in this case in the base of the transistor, and the amount of charge is proportional to the current. So we have a diffusion capacitance that turns out to be proportional to the current through our transistor or through our junction. The other capacitance that plays a role is the so-called junction capacitance, which is due to the fact that we have a space charge in the depletion region. And this is always there, but it is dominant then in low bias or reverse bias. It is proportional to the inverse size of the depleted volume. So it goes like 1 over square root of built-in voltage minus voltage. So, and then I can also write the same thing like this, or some constant C0 times 1 minus V over V built in to the negative 0.5 in the depletion approximation. So in a real diode, it'll be slightly different. Now it's instructive to look at a SPICE model for a transistor here. This is a model card for a SPICE for a transistor, the 2N222, which we I think is the same one that is used in the exercises. A very commonly used transistor. So this is a model card. There are many more effects than we've seen so far, but some of them we know. This is the gain, the beta of this transistor. This is the early voltage. We have the saturation current and so on. But what we're interested in now, sorry, are these constants here that are relevant for the capacitance calculations, and these are for the junction capacitance. So GE stands for the emitter junction, and there's also this constant here. So now, if we look at the base emitter capacitance, then we have these two contributions, the junction capacitance and the diffusion capacitance. The junction capacitance is expressed in this way, which is the same expression that we had on the previous page for the depletion approximation. This is typical for what is often done in SPICE, that you have to take a model and use the formulas that you have in there, but you modify the parameters a little bit. So in this case, instead of the built-in voltage, which would be something, you use a phenomenological parameter here. And in this case, it turns out to be 1.1 volt. The power in this case is exactly 0.5 actually. So this is the junction capacitance, and then the collector current multiplied by some constant gives you the diffusion capacitance, and this constant is usually expressed in terms of a time divided by the thermal voltage. So if we now take these values from the model and put in something realistic, or the model values and the current that we use for the simulation, then you get, for the base emitter capacitance, 50 picofarad for the junction and 150 picofarads for the diffusion, which is typical because in forward bias, the diffusion often dominates. While for the collector emitter diodes, which is in reverse bias, you get this expression here, the sign for the current, for the voltage changes, of course, because the voltage here is counted in the other direction. And here you only get 4 picofarads. So this capacitance is much larger, which is typical, and it dominates the transition frequency. And then if you use the formula that we found for the transition frequency, 1 over 2 pi times GM over CBE, which, or this, you can neglect here the CBC. And you put in the expression for GM, which is IC over VT from this exponential law. Put in the number 10 milliamps, 25 millivolts for VT, and the 190 picofarads. Then you get a transit frequency of roughly 300 megahertz, as we've seen in the picture, which of course was a simulation of just this transistor. It's interesting to note that when you are in the region that you can completely neglect the junction capacitance and have basically only the diffusion capacitance left, then your transition frequency becomes basically independent of the current. It cancels here, and you're left with 1 over this tau f, which is therefore also called the transit time, or transition time, or transit time. So this can be identified as a time that the charges need to travel, to diffuse through the base. So this is sort of a built-in speed limit for any bipolar transistor. Okay, the last thing I just want to mention briefly is we've seen two different configurations now, or 3 different actually. One where the emitter was grounded, one where the collector was connected to a fixed potential. There's also an amplifier that uses the common base configuration. So you attach the base to a constant potential, and then you consider the emitter your input. So you can, in this way, you could view the emitter as a current input for your amplifier, and then the collector current is basically the same as the emitter current, but you have a very, very small input impedance. So this transistor fixes basically this voltage, and then you can send in currents with a very small impedance, which is often useful. You can also turn this into a voltage amplifier by putting a resistor here and defining the current that flows into the base by the voltage difference between the input and the base. So here you have the current is the difference between the emitter and and the input divided by this emitter resistance. Now you have a voltage amplifier, and the advantage of this type of amplifier is that you have no Miller effect here, because the capacitance, so this point here sees essentially the base emitter capacitor, and there's no Miller effect here. So this is this can be used at very high frequency as an amplifier. Okay, this is it for today. Thank you, and see you next week again. Questions are, of course, possible now.